Hi everyone, welcome to Astronomy 236. This is our third and final lecture bite of week 2. Today we'll be asking and answering the question, what are stars, and in particular the sun, made of? Now, I want you to recall back to our lecture last week on light. If you have elements in relatively diffuse gaseous form, and you spread out the light emitted by these elements, either through a prism or through a grating, you can see that the elements produce sharp bands of very particular colors, and these are the fingerprints of the different elements. If you plot them on a graph like this, where on the y-axis you're showing the brightness of every given color or intensity of every given color, and on the x-axis you're showing the wavelength. Each different color of light is a different position on the x-axis. You can see spikes that end up at different positions, and you can predict these spikes based on either using the Schrodinger equation to derive what the energy levels are for the different electrons, or you can measure them in a lab. And different elements produce different colors that make them uniquely identifiable. These are the fingerprints of the elements. Also remember that if you have a more dense material, it doesn't produce sharp lines. It instead produces a curve that looks a little bit like this. So it produces this smoothed out curve because everything's a little bit smeared together because things are so close together that electrons from different atoms interact with each other and tug and pull and cause those energy levels to basically smear out into this big, large, continuous curve. So now I want you to take a look at what the spectrum of a star looks like. So this is the sun. And the first thing that you'll notice is that overall, the shape of this curve is very similar to these black body curves caused by dense material. You can see this overall slightly skewed bell shape where it sharply drops off at the low wavelength side. There are very few light particles coming out in the ultraviolet, and then it more slowly decays out in the infrared on the higher wavelength side. But the other thing you'll notice is that even though the sun looks like a black body, because it's a very dense ball of stuff, it also has little sharp lines. Now these lines are not exactly like the ones that you saw in the emission spectra, in the arc lamp spectra from hydrogen and neon, but they're caused by exactly the same process. These are the fingerprints of the elements. We see them in reverse here because the sun is hotter on the inside, which causes the denser overall black body shape, and these diffuse gas particles on the outside are blocking that light, and essentially with the same process as we had for those spectral lines and energy level transitions in the atom. So we have the fingerprints of the elements to see what's in the sun. So let's take a look and figure out what's there. Here's a closer look at what the solar spectrum looks like. So instead of plotting it on an X and Y axis, this is stacking lots of different bands together. So what you'll see is that there's a lot of continuous color. That's the overall rainbow that you see. And the top of the figure is redder wavelengths, obviously colored that way in this image. And on the bottom of the figure are the bluer wavelengths. And what you'll notice is that there are these little dark bands scattered throughout. These are absorption features caused by those elements, exactly like those sharp lines that we saw in hydrogen gas emission labs. And here's what a zoom in of that spectrum looks like when I plot it in the usual way, where on the y-axis I'm showing the brightness of every color, and on the x-axis I'm showing the wavelength. So a lot of these lines here, a lot of these absorption features have been labeled. So just reading off here, I see absorption from nickel, iron, calcium, manganese, iron, titanium, hydrogen, silicon. So evidently there's tons and tons of different elements that make up the sun. But which ones are the most important? To answer that question, we have to figure out a way to go from the spectra, to go from the strength of these lines and their frequency and how often we see them for each individual element, and turn that into relative proportions. And the first person who did this in astronomy is Cecilia Payne, who later married and became Cecilia Payne-Gaposchkin. So what I want you to do is recall how these different fingerprints of the elements are produced. In hydrogen, when you have an electron that's in the n equals 3 level, it can fall down to the n equals 2 level and emit light with a very precise energy that's equal to the difference of those two levels. And that's how you get this red bar of the n equals 3 to n equals 2 transition over on the right-hand side here. But in order to create this bar, you have to have electrons in the n equals 3 state to begin with. Otherwise, you wouldn't have that the opportunity for it to fall from n equals 3 to n equals 2. So to figure out how to take the spectra that we observe and the strengths of those lines that we observe in the sun and turn that into relative proportions of what the sun is made of, we have to know how many atoms were in that state to begin with. And that was what Cecilia's calculations mostly focused on. So her PhD thesis gave this table to show the relative strengths of all these elements. She calculated, as a function of the temperature of the star, how many elements should be, or how many electrons should be in different states and different energy levels, how often we should expect to find them there. She also calculated how often we should expect to see elements that are really there and have electrons to begin with, as opposed to elements that have been ionized and have no electrons to fall into different energy states and therefore produce spectral lines. And she went through all of these calculations, and here were her results. What she found was pretty surprising at the time. She found that hydrogen and helium were by far the largest constituents in the sun. And all of the other materials like lithium, carbon, sodium, manganese, magnesium, these were all thousands to millions of times less strong. These numbers that she's listing here are exponentials. So hydrogen is 10 to the 11 times more abundant than her reference, and magnesium is only 10 to the 5.6 times. So her calculation said that there's 1,000,000 times more magnesium than there is hydrogen in the sun. These numbers have actually held up pretty well. Here's the most up-to-date version of this table that I could find from 2009. And you'll see that hydrogen and helium are indeed the most abundant elements by a lot. The numbers have shuffled around a little bit. She wasn't quite precise on everything, but more or less she got the right answer. The sun is overwhelmingly made up of hydrogen and helium. Now, this was a really surprising result at the time. The prevailing wisdom in 1925 was that the stars were made of about the same mixture of elements as the Earth was. So if you took the Earth and you ground it up into a powder, and you counted how many atoms of hydrogen you had, and how many atoms of magnesium, and how many atoms of silicon, and how many atoms of iron you had, so the astronomers believed that that should basically be the same as what you would do if you did the same thing for the sun. And the only difference is that the sun was much hotter and therefore was made of gas and was glowing. But what Cecilia Payne found is that compared to the Earth, there was much more hydrogen and helium in stars. So when she presented her PhD thesis to her committee of advisors, they were taken a little bit aback by this. This was an unusual result. It was pretty strange, and it went very much against the prevailing wisdom. So they advised her to be a little bit cautious in presenting these results, and to maybe leave them in, but to say, I don't necessarily believe what I found about hydrogen and helium. My calculations, I think, are right, but maybe there's some other factor that I'm missing, which is causing me to get this wrong. And this quote from her thesis is how she did that. She says, although hydrogen and helium are manifestly very abundant in stellar atmospheres, because we do see those lines, the actual values derived from the estimates of marginal appearance, the spectral lines that she used to make these calculations, are regarded as spurious. She thinks that something else must have caused them to have these extraordinarily high values compared to all of the other elements. So Payne made these changes to her PhD. She eventually was awarded her doctorate. Everyone was very impressed with the rest of her thesis, whether or not they really believed the results about hydrogen and helium or not. And over the next couple of years, people started to realize more and more that maybe Cecilia Payne had a point, and maybe hydrogen and helium were in fact very abundant in stars. And pretty quickly after she published her thesis, this started to become commonly accepted that stars were made mostly of hydrogen and helium throughout the galaxy and throughout the universe, and that most of the matter in the universe, therefore, was made of some of the lightest weight elements. Eventually, Payne had a long and illustrious career. She became a professor at Harvard, and when she was in her last year of teaching classes at Harvard before she retired, my PhD advisor had the opportunity to be in that class. And at the end of the class, she had one final lecture where she talked about some of the things she had learned over her career and some advice that she had for the next generation of scientists. And one of the things that she said was, if you make a discovery, present it boldly. Don't necessarily hedge your bets, because if you're bold and you're right, people will believe it and they will give you all of the credit for it. But if you're bold and you're wrong, then that's okay too, because all that will do is it will encourage other scientists to come in and carefully look at your claims, and it'll very quickly show whether or not you were right, and it'll correct the record. So either way, science proceeds quickly when people make bold claims. We have to wonder just how much of this advice that she was giving was impacted by her own experience in her PhD thesis, where it took several years after its publication for people to really recognize the implications and believe that indeed most of the universe is made up of hydrogen and helium.